I hope you're doing well. I'm very excited today to make this video about the earliest atomic models. And 2 years ago, when I made this YouTube channel, I made a video about the ancient Greece opinions on matter, and then made a video on the chemists and their experiments to hint the existence of the atoms, and also about the electron discovery and measurements of the charge to mass ratio of the electron by Joseph Thomson, and even measurement of the charge of the electron by Robert Millikan. But now at this point, we are ready to talk about the earliest atomic model, which is the Plum pudding model of J.J. Thomson. But so there is a chain of thoughts from Thomson to William Thomson or Lord Kelvin, Helmholtz, and even to Descartes. So we're going to talk about them in detail in this talk, and I hope that you stay with us in this topic. I mainly divided this talk to three major parts. The first part is about Descartes and the knot theory by William Thomson and Helmholtz. And the second part is about Thomson's challenges in his atomic theory. And the third part is about Thomson's solutions to the challenges, or how did he manage to explain his atomic theory based on the evidences which existed at that time. So let's go to the first part, and Descartes and knot theory. As we previously mentioned, the atomic theory or nature of matter was mostly in the territory of philosophy. So it was discussed in a context of natural philosophy. But eventually, physics separated itself from philosophy by going into mostly mathematical argument and geometrical argument. Like in order to explain a certain physical theory, you didn't have to use a literature like Aristotle, which was mostly philosophical questions and philosophical features of matter. But mostly they were trying to explain everything based on geometry, because geometry was a part of mathematics that was really trusted, and it was kind of trivial, the Euclidean geometry. And that's where the first attempt of any theory is mostly try to approach the problem by the geometrical approach. So let's go to Descartes. Descartes is a very famous philosopher in the Renaissance time, and I really don't want to talk about Descartes in detail here, because his contributions to philosophy and even physics and science is huge. But what I want to mention is that he also had a theory of matter. He had a theory of matter, and he didn't believe in atomic theory. But what he was mostly trying to do, maybe I move my image here. So what he was trying to do is basically use mathematics and geometry to explain physics, to explain the motion of the planets. There is a book that Spinoza wrote about Descartes' philosophical ideas and also physics ideas, where he's stating that he didn't believe in atoms, so he was not one of the supporters of atomic theory, and he also didn't believe in voids. So these voids and atoms from Democritus, they come together, but Descartes didn't believe in atomic theory. So now we know that atoms are kind of there. Descartes was wrong, but why was he a progressive person? Not only because he kind of invented this whole analytical geometry context from Cartesian coordinates, so how he transformed algebra into, or connecting algebra to geometry is really amazing. But he also believed in a kind of field concept. So he was one of the people who had this notion of field, not as we know today, but he believed in a vortex type of theories that, for example, if you look at this illustration here, people were trying to explain why the planets are moving around the sun. And nowadays we know it's about the laws of gravity. But he was before Newton, and he had this vortex theory that the sun and planets are moving into kind of vortex current. And he had this intuitive idea from the fluid, so you can see the vortex forms and everything follow a trajectory. But he was a kind of pioneer to believe that the field notation or field or kind of elastic impact of a physical effect is something that you should explain the motion of the planets with that. But he didn't believe in atoms or voids, and he also believed that the matter is divisible to infinite level. So he was basically saying that the matter is divisible to infinite level, and you can always divide the matter into the smaller and smaller part. And so therefore he believed in a continuous matter theory. About 300 years after Descartes, an English physicist by the name of William Thomson, his name was also Thomson, same name as J.J. Thomson, but William Thomson, or Lord Kelvin, as he's famous now. And he's so famous because there is also a second law of thermodynamics in his expression. It's called Kelvin expression of the second law of thermodynamics, which is equivalent to Clausius expression, which is stating that this is his original code, that it is impossible by means of inanimate material agency to derive mechanical effect from any portion of the matter by cooling it below the temperature of the coldest surrounding object. Or if you want to simplify it, he was saying that it is impossible to make a machine which converts 100% of the heat to work, because then you can violate basically the heat transformation from the cold object to hot object. That's how it can become equivalent to Clausius expression. But he's very well known in thermodynamics. He was one of the founding fathers, along with Joule, Clausius, Helmholtz, and Gibbs himself. And there were other people, but Carnot. And so we also know him with the unit of temperature, absolute temperature, Kelvin, which was also one of his contributions. But he also had an atomic theory. So a few years before, a German physicist, Hermann Helmholtz, he's also very famous. He was one of the founding fathers of thermodynamics, and he had a potential in thermodynamics named after him. And he also had theories in electricity and circuits, and such an extensive person in terms of knowledge. But he also worked out the mathematics of moving a vortex inside of a perfect fluid, or a fluid without any friction. So Lord Kelvin, or Sir William Thomson, he wrote an article, and let me just read it. After noticing Helmholtz's admirable discovery of the law of vortex motion in a perfect liquid that is in a fluid perfectly destitute of viscosity or fluid friction, the author said that this discovery inevitably suggests the idea that Helmholtz rings are the only true atoms. So it's just simply stating that these rings and the vortex inside of the rings are representing atoms, and this is the atomic theory. And this is how basically radiation and matter interact with each other. So again, the idea of field was used here. So you can say this is how they're connected to Descartes. They have this notion of vortex, but these vortex are representing atoms. Kelvin put one step forward, and he was even trying to explain, why do we have different atoms? Why do we have different types of elements? Why do they have different properties? And he did it with one of his co-workers, Peter Tate, and he was a mathematician mostly, and he's one of the founding people of the branch of topology in mathematics, which is concerned with how can you define different properties, like kind of geometrical independent properties, by twisting object in different ways. And he had this theory of knots. So they had this theory of knots together, and they were simply stating that if you tie different ways, if you tie this vortex in different way, these different knots are representing different characteristics and different properties. Therefore, these are different atoms. So he was not trying to say the vortex is basically divisible like Descartes, but he was saying that no, I mean, you have different ways that they can tie. So therefore, you just create this atomic diversity. And nowadays, we know this theory is wrong. I mean, there is electrons inside of the atom. But the methodology is so interesting. He was trying to explain diversity based on some simple underlying principle. And nowadays, if you are familiar with the string theory, or the way that the string theory is trying to explain a standard model of particle, it's basically stating that different particles are different vibration modes on the strings, and these strings are also living in kind of different compacted manifolds in different dimensions. But the underlying principle is that there is like this kind of topological and geometrical features of them that make this characteristic, that makes the characteristic distinct feature of the elements, or fundamental particles. And their theory was also similar to that. So in that manner, it is very interesting. It is very interesting, and it shows the imagination sometimes is very strong, and you might be 1 century back in time, but in future people would go back to, again, similar ways, because again, geometry is a very important way that we can express this kind of diverse ways of making things. Okay, but the interesting connection between Kelvin and Tate theory on the atoms was their connection to J.J. Thomson on his master thesis in 1882 on Cambridge. He wrote this dissertation on the motion of the vortex ring, and he initially proposed an atomic theory when he was young, and then he later discovered the electron cathode ray discoveries, and then he measured mass to charge ratio of the electron, and therefore he changed his mind because of the empirical evidences that he found, and therefore you can say Thomson had the evolution of thought from this kind of vortex ring to his own model. But therefore it looks like that he was highly encouraged by the theory of William Thomson about this vortex and this diversity. Joseph Thomson is a very interesting character, and he also had a son, George Paget Thomson, and they were both awarded the Nobel Prize in Physics. The father was awarded because he measured the charge to mass ratio of the electron, and he proved the electron is a particle with a specific charge to mass ratio, has like particle properties, and his son diffracted the electron. So by diffracting the electron, he accelerated them, and then he crossed them by a thin foil, and then by observing diffraction patterns, it kind of confirmed this wave-particle duality proposed by Du Broglie. We will come to this point because we are going forward in time. We'll talk about this experiment because it's very interesting and important. But it's interesting that the father kind of proved the electron is a particle-like entity, and then not proved, maybe proved is not a good word. Proved is not, is for mathematics. For physics, I have to say he found evidences that the electron is like a particle, and then his son, 30 years later, found that the electron confirmed basically that the electron had experimental behavior that can be explained by the wave nature of the electron. Okay, now we go to part 2 and the challenges that he has. What challenges he has and how did he start to manage to propose an atomic theory? I have to say that Thomson was the last generation of the physicists who set the stage for quantum mechanics, but he was not using quantum mechanics himself. He was trying to use classical physics to explain this theory of atom. But his atomic model is a classical model. So in that sense, has the respect that he was trying to explain the atomic structure based on the principles of electrodynamic and mostly equilibrium in electrodynamics. So he was like a kind of classical physicist, but the generation after him, including his own son, they came up with quantum mechanical framework and quantum mechanical solution. So maybe he was just, not at the time where quantum mechanics was developed initially by Planck, Einstein, Bohr, and then, setting a stage to make a proper atomic theory. But in fact, he was trying to use classical physics. Okay, now let's talk about the problem of the stability of atom. As we previously mentioned, we had a problem to explain why the solar system model doesn't work for the atom, because in electrodynamic, an electron or any charged particle that is moving inside of the electromagnetic field, anytime that those particles accelerate, they experience a drag force, and this drag force basically reduces their energy and their orbital energy, and they eventually having this spiral motion downwards. So let me just show you this animation that the electron, is just, sending this radial wave out, and, as eventually these waves are coming out in a symmetric wave, and the particle just collapses into the positive center. So now the problem was that you can calculate this time by just simple classical physics calculation. You can calculate the power radiated by the electron, and then also for the energy, the total energy of the system, you use virial theorem. For the total energy of the system, you use virial theorem. Then you can calculate this characteristic time, which is the energy divided by this power, and then that would be around 10 to the power of minus 11 seconds. So therefore, you cannot explain why the atoms are stable. So that was the first challenge. The second challenge was the light spectrum of the elements, or absorption or emission spectrum of the elements, which was like a fingerprint for the elements. So we previously mentioned that in the 19th century, that was a big time for manipulating electricity and circuits, and people learned how to make high voltage and high current. And then eventually they started to ionize hydrogen, and they eventually observed the spectrum of the particle. But previously in the 19th century, they also see this absorption pattern. And the question was that how can we explain how the light is absorbed? So you can see here, imagine if you put all the spectrum of the light inside of the atom, only a few of them are coming out. So what's really inside? And that's basically a very, very primary form of a scattering experiment, because you're sending some projectile and then the output is responsive to what is happening inside. Or the other way is that you connect the atom to a voltage. I mean, it's just a kind of illustration, but you can apply high voltage or try to heat it up, and they start to radiate. And again, why do they radiate in certain way? So if you look at this spectrum, which is this one is the radiation spectrum and this one is the absorption spectrum, is that they look like a barcode. And barcode, what barcode is doing. Barcode is for each item is like their characteristic barcode that the system can realize this is fruits, this is in the supermarket, you can see what is the application of the barcode. And the atoms also had similar things to the barcodes. And the question was that how can we explain certain frequencies? And the classical theories were basically predicting that all the frequencies should be involved, because in classical physics, you're allowed to basically vibrate in most of the frequency. So the sudden observation that there are some discrete missing frequency and there are some discrete specific frequency in the radiation spectrum of the particles, people start to think about this is one of the very first visualization of how things are quantized, how things are not all possible things, but there are certain allowed things. This is probably the nature of quantum mechanics. But J.J. Thomson proposed a way in his atomic model in classical physics to explain why do we have this quantized spectrum. And he didn't have quantum mechanics, so he wasn't ultimately right. But again, his theory was using a lattice of the electron in order to say that there's some frequencies that you can resonate them, and then this resonating is those corresponding frequency into the light spectra. The concept of the spectrum of the light was discovered 1 century before J.J. Thomson by Joseph von Fraunhofer and Andres Angstrom. So they were the first people who observed this kind of absorption pattern of the light that was coming from the sun and the stars, and that was basically the birth of astronomical spectroscopy. Then they started, but they were the first one who found out that this discrete pattern is something strange. And look at the time that he was living. He was living from 18th and 19th century, and this was quantum mechanics, but they needed 1 century to completely figure out how. And the radiation spectrum was discovered by Gustav Kirchhoff and Robert Bunsen, German physicist, and Robert Bunsen and Kirchhoff together, they discovered new elements based on this method. So they are the founding fathers of spectroscopy in material physics. This one was in astronomy, and this one is in material physics. And nowadays, people use the similar techniques using the absorption and radiation pattern of the elements to identify what elements or what component they have. And Robert Bunsen discovered cesium. Cesium right now is the element that we use in defining the standard unit of time, or second. So the cesium is defined as the duration of the 9 billion periods of the radiation corresponding to the transition between two hyperfine levels of ground state of cesium-133 atom. So this cesium, however, I'm just saying that today the unit of second is defined based on the number of the frequency of the electron inside of the cesium atom. So I mean, it's just interesting that cesium was found by Robert Bunsen by using a spectroscopy of the element. So I mean, I'm just saying that chemistry was getting very, very strong with this empirical evidences that they found, and it all gave these clues to Joseph Thomson to construct the theory. The third problem was the alpha-beta emission that was discovered by, actually originally by Henry Becquerel. Henry Becquerel, there was a rainy day, and he put his sample in the drawer, and there was no light. But then he later found that the sensitive film or sensitive paper basically captured the radiation, a very, very strong radiation from that sample. And then this field was expanded by Marie and Pierre Curie. They got Nobel Prize for that in 1903 for the discovery of basically radioactivity. But this alpha-beta emission, as they decompose it into 3 components, was kind of mysterious because people couldn't explain why some heavy elements should radiate alpha-beta particle or even a very strong gamma-ray electromagnetic radiation out of them. It was a mystery, and it was probably very important for Joseph Thomson to explain why do we have this phenomenon. So if you think about it, Thomson was really trying to make a scientific theory because he had these 3 basic challenges in front of himself. And you can see the picture of Marie Curie and Pierre Curie in the lab. So part 3, solutions and Plum pudding model. Plum pudding model is the popular name for Joseph Thomson model, and apparently he didn't use this term by himself. It was suggested probably by the early magazines, popular magazines, to kind of connect this picture of this very favorite British dessert into the atomic model. So maybe I can show you the picture of the plum pudding dessert. This is something like that. And it mostly corresponds to his proposal of the theory in the 1904 paper in the Philosophical Magazine. His previous paper was also in the Philosophical Magazine, and the title of it is representing on the structure of the atom, And I have to say that this term, Plum pudding model, is a little bit misrepresenting, I think, the picture, because in his model, the electrons have a little bit of freedom to oscillate around. And if you think about a cake or any kind of this type of dessert, the electrons are not allowed to move that much because it's like a solid form. So mostly J.J. Thomson was thinking about a kind of liquidish behavior of the positive charge, and then the electron has a little bit of a space to vibrate.
Plum pudding. Plum pudding.
Okay, so this paper is a very important paper. I was really happy to read it and highlight some part of it. I don't want to definitely go into the detail, it's just really boring. But, I just tried to use his own, because he was also English, so we can read the original text without translation. So I'm going to read this. An investigation of the stability and periods of oscillation of a number of corpuscles. So this word corpuscles, he used that instead of electron. He wasn't using even the name electron. The name got used later on and popularized, but he was using this word corpuscles, which means a small cell, small unit, arranged at equal intervals around the circumferences of a circle. So his model was basically trying to use, again, a kind of geometrical approach into the atomic model. You can see equal intervals around the circumference of the circle. And with the application of the results to the theory of atomic structure. It's interesting. It's a kind of very modest phrase to say with application of the results to the theory of atomic structure. And you can even see his original paintings that he was also trying to use all sorts of geometry to stabilize these rings and even like a polygon structure with 6 vertex. Anyway, so let's go into the paper and read it. Anyway, I want to say that anyone had this kind of geometry And this is something interesting. This is probably one of the things that I wanted to emphasize, that this geometry was always important. And you can see that Kepler divine geometry that he was trying to explain the motion of the planets is kind of similar to what Thomson was trying to do with the electrons inside of the atom. So it's very, very strong. And nowadays, even in material physics, you can see that people are talking about lattices and how geometry is determining the physical feature of the matter. Okay, I don't want to go into the detail, but just highlighted some of the points to show you the essence of J.J. Thomson theory. So the first one, the most important one, is probably this uniform positive electrification, or this uniform positive charge inside of the atom. So that was his proposal. And nowadays we know it was because he wanted to stabilize atoms. So I mean, in his idea, there was no way to put all the positive charge in the center. And he already knew the ratio of the mass of the electron to the mass of the atom, because he measured the charge to mass ratio of the electron. And previously, the charge to mass ratio of the hydrogen ion also was found. So therefore, you can conclude that the mass of the electron is around 1/2000 of the mass of the atom. So to Thomson, assumption was based on the fact that the mass of the electron is small compared to the mass of the atom. But the number of the electron inside of the atom can be large. So imagine that if something has 1000 electrons inside of that, that's a comparable mass to the mass of the atom, and they're all kind of electrons. But we will see that he's suggesting numbers around 100 to 100 maximally, because he has difficulties to figure out how to stabilize very, very high number of electrons. The other word is that when in equilibrium, so he was mostly talking about equilibrium, electrical force equilibrium, and therefore the equal angular intervals was something to make this equilibrium. And he's here saying that if the corpuscles are addressed, this attraction must be balanced by the repulsion exerted by the other corpuscles. So it was basically a mixture of positive charge and a mixture of attraction and repulsive force that could hold the system in equilibrium. So he was making this kind of first divine atomic theory, but it was very, very accurate compared to, for example, what Kepler trying to do. I just want to show you that how much calculation he did, and most of his calculation is based on accurate mathematical calculation. So therefore, it's not like a philosophical model, but it is based on geometry. So he was trying to solve the problem of stability by sometimes rotating those rings or introducing some electron at the center to stabilize the atom. So here, for example, it says the 5 corpuscles are unstable with one plane unless the angular velocity exceeds a certain value. The arrangement is stable, however, when angular velocity is large. And the other way that he introduces that when the number of corpuscles exceed 8, the number of the central corpuscles required to ensure stability increases very rapidly with the number of corpuscles in the ring. And you can see that this n represents the number of the corpuscles in one ring, and then to stabilize them has to introduce this kind of center electrons or corpuscles at that time. And as you can see, when it's going up, it should go up rapidly. When it is around 20 to 30, 40, suddenly from 39 to 100 and 232. So basically, he was trying to see how to stabilize them, but the output was interesting because now he could interpret those things in certain ways. And even though this is like imagination today for us, but it was a very interesting topic. Let me read this part for you. It's about the application of this theory. So, I mean, he believed that his theory was a theory. He said it's a kind of geometrical theory, but there is an application of the preceding results to the theory of a structure of the atom, on the structure of the atom. So he's modest enough to say, this is just a model, this is a geometrical model, and it has an application on the structure of the atom. Let me read this part for you because it's very interesting, all of it. We suppose that the atom consists of a number of corpuscles moving about in a sphere of a uniform positive electrification. The problem we have to solve are number one, what would be the structure of such an atom? How could the corpuscles arrange themselves in a sphere? And 2, what properties would this structure confer upon the atom? Number 2 is interesting. Number 2 is chemistry. What properties the structure confer upon the atom? How to make different atoms? The solution of one when corpuscles are constrained to move in one plane is indicated by the result we just obtained. The corpuscles will arrange themselves in a series of concentric rings. This arrangement is necessitated by the fact that a large number of corpuscles cannot be in a stable equilibrium when arranged as a single ring, while this ring can be made stable by placing inside it an appropriate number of corpuscles. When the corpuscles are not constrained to one plane, but can move about in all directions, they will arrange themselves in a series of concentric shells. So, I mean, that was the solution. If they are in one plane, there are ways to stabilize them. If they are in different planes, there are ways to stabilize them. But in most of them, there should be a kind of symmetry, that they should have the same center. They should have the same kind of symmetry. And that's kind of spherical symmetry that he believed the atom should have. This spherical symmetry is very powerful, that we think atoms should be kind of a sphere-like object. And, we know the planets are like that. It's interesting in a very, very large scale. Again, it's a gravitational equilibrium, that everything goes into a kind of spherical shape, the planets, but you still see that there is some imperfectionism. But in the atomic scale, you expect them to be really, really like good and perfect. So let me read this part for you. This is just, just clues that he's saying. Atoms by this ring structure analogous in many respects to those possessed by the atoms of the chemical elements, and that is, in particular, the properties of atom will depend upon its atomic weight in a way very analogous to that expressed by the periodic law. So we already know about periodic law, and he's saying that the atomic weight is responsible for the properties, because then you can, because you know why? Because we have the number of electrons, and how to stabilize the electron, you might need a lot of electrons, and you're increasing the atomic weight. On this side, we suppose that the mass of the atom is the sum of the masses of the corpuscles it contains. So here is what he's saying. The sum of them is the mass of the atom. So he was wrong at that time. The majority of the mass is in the center, so that the atomic weight of an element is measured by the number of corpuscles in the atom. Okay. And a very interesting part. He's trying to explain chemistry, but he was actually writing this. The number of corpuscles in the outer ring N1. So the outer ring is what we know today as valence electrons, and when they determined by the conditions at n minus n1, and then try to explain as a function of n1. But n1 is the number of electron in outer ring, and he's correctly saying that this is chemistry. In the first places, we see that the various arrangements of the corpuscles can be classified in families. The grouping of the corpuscles in the various number of the family having certain features in common. Interesting, right? Certain features. Okay, so his solution for light spectrum was interesting. So as I said, he was looking at it as like a kind of resonating box when you scatter light, and some frequency is the resonant frequency, and he was trying to explain that. So he was saying that those arising from the rotation of the corpuscles around their orbits. If all the corpuscles in one atom have the same angular velocity, the frequency of the vibration produced by the rotation of the ring of the corpuscles is proportional to the number of corpuscles in the ring. And thus, in the spectrum of each element in the series, there would be a series of frequency bearing the same ratio to each other. And therefore, he was trying to explain these base frequencies are vibration modes of this system. And he already knew about this periodic table that was first proposed by Mendeleev, the Russian chemist, and he organized the elements. So at that time there was a certain number of elements that were known to them, but he organized them based on properties. And today we know this was not even completely correct. But the interesting it is that it captures the essence of periodic table, and therefore by the discovery of proton, everyone realized that this periodic is not because of the electron. Actually, it's because of the proton at the center. So it's true that the electron is balancing the proton, but the properties of elements is basically based on the number of protons. So the properties of the atoms is because of the properties of the proton, and then counterbalancing by the electron. But in Thomson theory, he was thinking it is all electron. The number of positive charges, there is not a positive charge. It's just a uniform electrically positive sphere. It wasn't he was not counting it as a periodic property. So here he's mentioning the name of even Mendeleev. Mendeleev's arrangement of the elements is also illustrated by the properties possessed by these groups of corpuscles. And now he's bringing these elements here. The first and the last elements of each of these series has no valency. So he's using the word valency. When atoms like the electromagnetic ones, in which the corpuscles are very stable, are mixed with the atoms like the electropositive ones, in which the corpuscles are not nearly so firmly held, the force to which the corpuscles are subject by the action of the atoms upon each other may result in the detachment of the corpuscles from the electropositive atoms and their transference to the electronegative. So he was even thinking about that the electron can transform. So he was would behave like the atom of a strongly electropositive element. So he was trying to explain electronegativity based on their tendency to lose the electron or the tendency to attract the electron because of the mechanical structure that these electrons are basically stabilized inside of that. So when the stability of outer ring gets very great, it may be possible for one or more corpuscles to be on the surface of the atom without breaking up the ring. It's interesting. He was saying that even some of them are losing those corpuscles. They are not destabilizing the whole atom. So he's saying that it would behave like the atom of electronegative element. So he was even trying to explain electropositive electronegativity of the atoms, or the tendency. For example, we know about that Linus Pauling got Nobel Prize in chemistry for explaining electronegativity 40 years after that. But Thomson had an idea about it. And for the third problem that he has, alpha, beta, and gamma emission, he's saying that the constituents of the atom of radioactive elements, or the study of the stability of the system of the corpuscles, has made us acquainted with systems which are stable when the corpuscles are rotating with an angular velocity greater than a certain value, but which become unstable when the velocity falls below this value. So he was to space explanation for why some atoms are losing huge chunk of themselves in the form of radiation. It's because their velocity is going down. So there was also a form of drag force or dragging mechanism in the atom by his theory. Thus, to take an instance, we saw that 4 corpuscles can be stable. So he's giving an example here. Let me go to the next part. That he's saying that, sorry, I have to move my image because I didn't make this arrangement that good, sorry. But become unstable if the velocity falls below this velocity. The corpuscles, in this case, tending to place themselves at the corners of the tetrahedron. Consider now the properties of an atom containing a system of corpuscles of this kind. Suppose the corpuscles were originally moving with velocities far exceeding the critical velocity in consequence of the radiation. So in the consequence of radiation from the moving corpuscles, so it was Bromistro along, their velocity will slowly, very slowly diminish when after a long interval the velocity reaches the critical velocity. It's very interesting, it's very obvious. He's saying that the kinetic energy gained in this way might be sufficient to carry the system out of the atom, and we should have, as in the case of radium, which was studied by Becquerel, Marie, and Pierre Curie, a part of the atom shut off. That was the explanation. It was, again, interesting, very mechanical, very classic. But now we know it's about weak interactions, and it's interesting. It's just crazy that need another century or another 50 years to really study those things on the proper knowledge. So sometimes it's just the time. So, people like Aristotle, if they were born in the time that technology was better, maybe they would definitely would find the correct theories. And the next step now, we come to the final point that, after he suggested all of this in his theory, he didn't really specifically say that he's proposing an experiment to confirm it. So one of his own students, they will come with an experiment in the following years after his theory. So his theory is for 1904, and Rutherford and some people with Rutherford, they start to work on this experiment of scattering alpha particle from the atoms to confirm this theory. And if you have two major theories, one that there is a center and then there is like a uniform positive charge, then this alpha particle should respond. So these alpha particles were discovered earlier by Becquerel, so they were new. So they just about to do the first scattering experiment of the century. So we're already talking about light scattering. The spectrum of the particle is basically like a light scattering. So frequencies of light comes in and they go out. But at the same time, the alpha particle, they definitely have a particle nature in contrast of the electromagnetic wave. So we were about to do the first electromagnetic and also particle experiment. So one expect that you have two major results from that. If you have a uniformly positive charge and then you have a uniform kind of distribution of the electron inside of the atom, then you expect the alpha particles are not gonna disturb or scatter too much. They're gonna go. And the example of it is like if there is a napkin and you throw heavy balls, you don't expect the napkin to kick back to the heavy ball, because heavy ball is very heavy. So these alpha particles were like heavy balls, and they were thinking that the atom is kind of dilute enough to be like a napkin. And we said that there's some good motivation for people to not want the solar system model inside of the atom because of these Bromistro long and the problem of attraction. Because if you put something in the center, it is kind of hard to stabilize this whole system, and you should have a very crazy radiation. So people were not willing to take that, but apparently that was actually the correct theory. And the reason that the atom is not like a solar system is because there's quantum mechanical constraint on that. So you need quantum mechanics to explain why did we have the kind of stable atom, but at the same time having this positive charge at the center. But the idea is that now if the whole mass is in the center, and then if you put these alpha particles on the way, only a few of them are going to be scattered. It depends on the size. Actually, they later found out that there are only a few of them are scattered. So they concluded that the center of the atom should be very small. But imagine if the center of the atom is very large, then the majority of them should be scattered. It's still very different with the Thomson model, because Thomson model was predicting kind of uniform transparency or uniform opacity, low opacity atom. So in his idea, the atom is kind of low opacity for the, his theory was saying that the atom is low opacity with respect to what? With respect to alpha particles. So they could use beta particles, but maybe beta particles are not that proper because they themselves are kind of light. So they wanted to use these heavy particles in order to see what would be the outcome. So that would be the subject of the next videos, and we will see the first scattering experiments, which was not only Rutherford scattering, because there was also this important scattering called Compton scattering, where the basis of what we do as elementary particle today. So if you understand them, if you understand their logic, then you can usually generalize them into this new heavy ion collision, for example, physics. So hopefully by the next videos, we will go into the next decades of the 20th century, where the eventual and gradual growth of the technology and quantum mechanics together form the foundation of today's life, because these quantum theories were absolutely changing the precision of the electrical devices. So quantum theory not only is explaining the atomic structure, but at the same time, all of the phones, all the laptops, and everything that we have today is influenced by the quantum nature transistors today. So they're all rooted in this critical time of the 20th century when they were trying to explain the atoms. And if you think that's a kind of crazy timing, it was only 1 century ago. It was 100 years ago. And compared to the all time that human being is living in this planet for 2,000 years, people really didn't know that much. because we didn't have that technology, or senses were not enough to detect those things. But eventually these devices and this pattern recognition and enhancing the senses that we have enabled us to come to the point to explain the atoms. So it was a long way. And maybe in the future, for centuries, we know about the atoms. But imagine only 100 years ago, this happened, and it is really, really close to us. So I want to thank you again, and to the next video, goodbye.